In this video, we'll be looking at some word problems that can be modeled with a sinusoidal function. So we're going to start off by recapping the general sinusoidal equation and what each value represents. And most of it will be a refresher. So to start off with, the sine function starts on the central axis, so right here on the sketch, and normally it heads upwards towards the maximum. However, if there is a reflection over the x-axis, which would make our a value, this value here, negative, it would head down to the minimum instead and have this kind of shape. Next, the a value, also ignoring the plus or minus, gives us the amplitude. And the amplitude is the distance from your midline up to your maximum or down to your minimum. We know that the period is the length of one cycle, and the period of a sine function is 360 degrees. However, we can't have every single word problem, every single scenario with a period of 360. So that results in this additional value that we haven't seen before. This is your K value. It represents a horizontal stretch or compression. It's not a focus to this course. For now, all I'm going to say is to calculate this K value, you take 360 degrees and divide it by the period. And that value is what we would put inside this big bracket where the angle normally goes. Next, we know the phase shift is the x minus d part, and it would represent where the start of your function is, so that midline point. And then finally, your central axis, which is that plus c at the end, is the line that is halfway between the max and the min. It also represents that vertical shift. So let's take a look at our first example. And you'll see a lot of wheel-related examples for these sinusoidal questions. A Ferris wheel has a radius of 25 meters. It rotates every 60 seconds. If passengers get on the ride at a point 5 meters above the ground, draw a sketch to represent the scenario and fill in the information. Okay, so I do have a little Ferris wheel on the side, and I'm going to take the information and think about what it might represent. So the radius is 25. So that means from the center of the wheel up to the max is 25, and from the center down to the lowest point is also a distance of 25. Now, if you already see it, that does actually represent our amplitude, because it's the distance from the midline to the maximum and from the midline to the minimum. It rotates every 60 seconds. So in 60 seconds, you start at the lowest point. 60 seconds later, we're back at that start. That means the 60 seconds represents the period. A passenger gets on the ride at a point 5 meters above the ground. That must mean when you get on the ride, you are at the lowest point. You can only go up from there. So that must mean that the 5 meters is actually our minimum. With that information, we should be able to get a pretty good sketch. So my minimum is 5. So I'm going to say here's 5. Now, if I know that my amplitude is 25, I can add 5 above, or I can add 25 above 5. So if I add 25, that'll take me to 30. And that is now my central axis. So y equals 30. Then I can add another amplitude of 25 to take us to 55. And that's my maximum. And now I have that good range of values where my function occurs. Now we are told that the rider is getting on at 5 meters, which means at time 0, this will be our starting point. Now with that in mind, I'm going to label here's my height in meters, and here's my time in seconds. Okay. It rotates every 60 seconds, so I know the period is 60. So what I can do, it doesn't tell me how many rotations to draw, so I'm just going to draw one. 60 seconds is here, so 60 seconds later, we should be back at the minimum. And now, using my knowledge of a sinusoidal function, halfway between the two minimums should be the maximum, and halfway between that, at 15 seconds, should be a midline point. And then halfway between 30 and 60 is 45. So there we are. I just took that period, split it into 4 sections, and a quarter of 60 is 15, so every key point occurs 15 seconds apart. So now I have a nice sketch. Okay, let's write the k value. This is new. So we take 360 degrees, which would represent the original period of the sine function, and we divide it by 60. And we end up getting 6. Now this 6, what it actually represents is in 360 degrees, the original period, we would fit 6 cycles of this Ferris wheel example. Okay, now the start. When I say start, I mean the starting point of a sine function, not at what value did we start. Sine function starts at the midline. So that's going to be my start at 15, 30, which means this midline used to be on the y-axis, but we had to shift to the right 15 degrees. With this information, we should be able to create a nice equation. Now, I'm not going to write y equals, I'm going to write something meaningful. So just on the side, I'm going to say let h represent the height in meters, and let t represent the time in seconds. So my equation will be h at t equals, we know the amplitude is 25. Now from my starting point, we are heading up to the maximum, so there is no reflection. My k value is 6. We're shifting to the right 15 seconds. So there we are. And then the central axis was at 30, so plus 30. And there we are. So amplitude of 25, here it is. The 6 came from our period, 360 divided by the period of 60 degrees. The t minus 15 came because our starting point was 15 degrees to the right, and the c value was the central axis at 30. All right, let's go to the next one. The depth of water off a pier at high tide is 7 meters and occurs at 8 p.m. 6 hours later, at 2 a.m., the depth of water at low tide is 3 meters. The next high tide is at 8 a.m. If this pattern continues, draw a sketch to represent the scenario for 24 hours and fill in the information. Okay, so we're given some important information to start off. High tide is 7 meters. That would be our maximum. We're also told the time that it occurs, which will be helpful when we sketch. Low tide is 3 meters. And this will allow us to get our central axis and our amplitude as well. But before we do that, I'm just going to create a little scale. Okay, so this is going to be our height in meters. And we need to do this sketch for 24 hours. So I'm going to put 24 hours at the end, 12, and just start labeling those key points. And this is the 24-hour clock, so 0 to 12 is AM, 12 to 24 will be PM. And that's time in hours. Okay, so our minimum is at 3. Our maximum is at 7. Halfway between that should be 5 for our central axis. And I could also see the distance from that central axis of 5 to the maximum of 7 is 2. Of course, I could also do 7 minus 3 divided by 2 for the amplitude, and 7 plus 3 divided by 2 for the central axis. All right, before I go to the period, I think it's going to be helpful to actually graph the points to identify what the period is. So the high tide occurs at 8 p.m. So 8 p.m. in the 24-hour clock is 8 plus 12 is 20. So that means at 20 hours, we should be at 7 p.m. So here's 20. There it is. And I'm just going to label it 20, 7, just because I don't have a nice grid. 6 hours later, we're going to have our minimum. So 6 hours later is 2 a.m., which does take us right here, and that's going to be a minimum. And then the next high tide is at 8 a.m. 8 a.m. is here. And at this point, it looks like every key point occurs every 6 hours. So I'm just going to quickly label, this is 2, 3, 6 hours later was 8, 7, 6 hours after that, so 8 plus 6 is 14. I'm expecting 14, 3. And because this is going to be a sinusoidal function, even halfway between the max and mins, I would expect that midline point. So halfway between 2 and 8 is 5. So at 5, 5. And then halfway between 8 and 14, so at 11, 5. Halfway between 14 and 20, 17, 5. And then after 20, so now every key point is occurring every 3 hours. So at 23 hours, I'm expecting 23, 5. And now I can connect my dots to draw this function, and then I can read the rest of my properties. Just going to continue like this. All right, so the period now. I'm just going to say start here at 2 a.m. and at 14, that's a 12-hour period. And that's just what I used as a cycle, but could have used anything. Okay, for our k value, we take the original period that should have been 360 and divide it by 12, so we get 30. In terms of the starting point, we need to start on the midline, so I'm going to use this point here at 15, 5, and I'm picking a starting point that does head up to the maximum, so we won't have a reflection. And if this is the point that I'm starting at, oh, sorry, it was 5, 5, not 15. So that means we're shifting 5 to the right. So now for our equation. In terms of the variables, we're going to have, let h represent the height in meters, and let t represent the time in hours. So we have h at t equals, our amplitude is 2 and no reflection because from the starting point we're heading up to the maximum. So 2 sine, the k value is 30. We're shifting to the right 5, so t minus 5. And then the central axis is also 5. And there we go. So here is a tide example that can also be seen as a sinusoidal function. Okay, let's try another type. An object is attached to the end of a spring that is bouncing up and down. At its highest point, the object is 8 centimeters below the ceiling, and at its lowest point, it is 20 centimeters below the ceiling. Initially, the spring is at rest and is stretched downwards. If in a minute the object completes 10 cycles, draw a sketch to represent the scenario and fill in the information. All right, so in terms of our axis here, we're going to have the time, and our time here, we're told about 10 cycles in a minute, so seconds would probably be best. And then for the y-axis, let's say the distance from the ceiling in centimeters. So
at its highest point, the object is 8 centimeters below the ceiling. So the maximum is going to be 8, but -8, because the way I gave us our x and y axis, the ceiling would be at 0. And the lowest point is 20 centimeters below, so -20. With that, we can get our amplitude and our axis. For this example, I'm going to change it up and I'm going to find my amplitude and axis first, and then I'll go to my scale and my sketching. So for the amplitude, I want to do the maximum minus the minimum and divide that by 2. So that would give me 12 over 2, which is 6. So there's the amplitude. For the axis, I'm going to add, so -8 plus -20, which is -28. Divide that by 2 and -14. When I do my scale, I'm going to be a little bit more rough with it. I'm going to say, here's -8, here's the central axis, and here's -20. Okay. Those are my special lines. I'm going to highlight them if that helps. And now, let's see what we're told. Initially, the spring is at rest and it's stretched downwards. Being at rest would mean we're starting at the midline and then we're being pulled down, so we're going to go down to the minimum. Now, what are we told in terms of the period? So in 1 minute, the object completes 10 cycles. So that means in 60 seconds, there are 10 cycles. So let's take that 60 and divide it by 10, and we get 6 seconds per cycle. And if we know the period is 6, then our k value would be 360 divided by 6, which is 60. So if my period is 6, that means 6 seconds later, we should be at the same starting position. So I think I'm gonna do 2 cycles this time. I know it doesn't say it, but why not? So let's say 6 seconds is here. I need to start and end at 6. Now, halfway between 6 is 3 seconds. Based on what I'm looking at, there should be another midline point. Halfway between 0 and 3 at 1.5, we should have that minimum point because we were told we're going down. Halfway between 3 and 6 is 4.5, and there we are. There's our sketch. And now it looks like instead of every key point occurring every 90 degrees, it's every 1.5 seconds. So I can actually continue my scale now, 7.5, 9, 10.5, and 12. And I'm just gonna jump up my lines every 1.5 seconds. And there we are. There's our sketch. So now our start, well, the start is on the midline. So I'm just gonna use 0, -14 as a start, but there is a reflection because we're heading down to the minimum. So there is no shift. Okay, let's say D represents the distance in centimeters, and let T represent the time in seconds. So we have D at T. We do have a reflection this time, and our amplitude is 6, which we can verify here from -8 to -14 is 6. We don't have a phase shift, so I don't have to worry about a double bracket. I'm just going to put my K value, so 60T, and then the central axis at the end for the -14. And there we are. There's another example that can be represented by a sinusoidal function. Let's try another one. This time we have a pendulum. So the pendulum of a grandfather clock is swinging back and forth. The horizontal distance of each swing from the center of the clock to the right and left is 6 centimeters. So that just means if this is the central piece, it's 6 centimeters to the right, so we can call that a positive, and 6 centimeters to the left, and we can call that a negative, just to differentiate between positive and negative. It takes 1 second for the pendulum to swing from the right to the left. If the pendulum is currently positioned to the right of the clock, draw a sketch and find an equation to represent this scenario. Okay, so it would make sense for the center to be our central axis, which is 0. So if we're at the center, let's call that 0. And then we're going to the right 6 centimeters, so maybe that's going to be our maximum. And we go to the left 6 centimeters, so that should be -6 for our minimum. So I'm going to write that information down as well. Max is 6, min is -6, which means our midline is y equals 0, and our amplitude, well, the distance from 0 to 6 is 6. Now, we're told that the pendulum is currently to the very right of the clock, which means we're starting at +6. And it takes 1 second for the pendulum to swing from the very right to the very left. So 1 second later, we're going to be at the minimum, which means it's going to take another second to get back up to the maximum. So the only points we don't have are the midline points, which should occur halfway between our max and mins. So at 0.5 and at 1.5. And there's 1 cycle of this function. So that means our period, now looking at this function, is 2 seconds. That's 1 full cycle. And I can continue this if I wanted to. If I wanted to add another one, just gonna go up every half a second and hop the lines, the 3 special lines we have. And there we go. There's another swinging motion of the pendulum. Now I am gonna label time in seconds and horizontal distance in centimeters. Okay, so I have a nice sketch. I have most of my information. The minute I know my period, it would be good to get the K value. So take the original period of 360 and divide it by 2 to get 180. Now in terms of the starting point, I'm going to choose this as my starting point on the midline, and I'm heading downwards, which means we will have a reflection. So I'll keep that in mind. And I'm going to write let D represent the horizontal distance, in centimeters, and let T represent time in seconds. So D at T equals, based on my starting point, I have a reflection because we head down to the minimum. The amplitude is 6. It's a sine function. My K value is 180, and I have to separate it from the phase shift part. And based on my starting point, which is 0.5 to the right, I'm going to write T minus 0.5 to show that shift. And then my midline is 0, so I'm not going to bother writing +0. And there we go. Another sinusoidal example. Last one. Arya is floating in a tube in a wave tank. At 1 second, Arya is at a maximum height of 14 meters. Okay, well that's great. We know the max already, given to us directly, above the bottom of the pool. At 9 seconds, Arya is at the minimum height of 2 meters. Draw a sketch and find an equation to represent this scenario. Okay, so I'm just going to do, maybe I'll try a nicer scale this time. So I'll say 2, 4, 6, 8, 10, 12, 14, 16. And this is going to be the height. And our minimum is 2, given to us directly. Our maximum is 14, given to us directly. Halfway, just visually, I can see it's 8, but for my midline, of course, I can also take the max and the min, add them, and divide by 2. For the amplitude, I can now count and see from 8 to 14, it's a distance of 6, or I can do max minus min, which is 12, divided by 2 is 6. So I have good information there. Now in terms of my time scale, we're told at 1 second, they're at the maximum, at 9 seconds, they're at the minimum. So I'm going to try to fit maybe 20 seconds. So we'll say 2, 4, 6, 8, 10, 2, 4, 6, 8, 20. And then halfway between that. Okay, so I want at 1 second. So here's 1 second, we're at the maximum of 14. At 9 seconds, we're at the minimum. Now we know there should be a midline point somewhere in the middle, so the middle between 1 and 9 is 5. Now, if that's not great for you, that you're just adding. 1 plus 9 is 10, divided by 2 is 5. There's my midline point. And now I can see to go from point to point, from key point to key point, is just every 4 seconds. So 4 seconds after 9 is 13. So at 13 seconds, I should be at the midline. Add another 4 seconds, so now we're at 17, and we're at the maximum again. I'm going to connect my dots. I know this will come down a little bit, and this will also head downwards. And there we are. So now, for my period, I'm just going to consider my period from max to max. So from 1 to 17 seconds, that's 16 seconds, which means my k value should be 360 divided by 16, which is 22.5. Now for my starting point, I'm going to use this midline point, although I can use this one as well. I'm just choosing the closer one, which means there will be a reflection. But I need my let statements first. So we have let h represent the height in meters, let t represent time in seconds. So h at t. I said there was a reflection because we're going down to the minimum from our starting point. The amplitude is 6. Sine, our k value is 22.5, and our starting point is 5 seconds to the right, so t minus 5. And our central axis, positive 8. And there we are. So for word problems, look at the words carefully, read the question, identify that max and min, and that should help you get your amplitude and your midline. There should be some information about the time component that helps you with your period, which helps give you the k value, so the original 360 by your period. Then pick a starting point anywhere on the midline, and that will dictate if there's a reflection and what the phase shift is. And once you have the equation, once you have the graph, you can answer follow-up questions. Like for this one, I can ask you, at what times is Arya at 8 meters? And I would know to look at my midline points and say at 5 and at 13. Or I can ask you, when is Arya at 12 meters? And then I'm estimating it based on my sketch. I might estimate here is 3 seconds and here is 15 seconds roughly. Or I can ask you, what is the height at a certain time? And I can use my sketch, or I could even replace my t value with that time and then punch it into my calculator. So that graph, that equation, it opens up some doors to us. But that's it for sinusoidal modeling.